Number 42. A group of 100 mice was accidentally released on a small island west of the state of Washington on March 1st, 2018. A University of Washington professor estimates that the island can support no more than 5,000 mice. On March 1st, 2020, the mice population had reached 1,200. The professor used a logistic model to predict the population on March 1st, 2025. He predicted this many mice. So this, like the problem says, this is going to be using a logistic model. And there's actually an equation for the logistic model. There's a differential equation you can use and a solved equation you can use. So I'm going to show you the solved equation, and then I'll show you a shortcut on the calculator that you can use using the differential equation. So this is the equation for the logistic differential solved. So the population as a function of t is equal to, this is kind of pretty big formula. It's the initial population times the carrying capacity, which is k, divided by the carrying capacity minus the initial population times e to the negative rt. R is the rate and t is the time, so it's like n of t, n of population depending on time, and then plus the initial population. So this is quite the formula, and we have a few constants we have to solve for. So really not that many. We just have to solve for r. So let's see how we can do this. So let's see. What do we know? We know that n of 0, the initial population, is 100, because it says that the group of mice was released. The 100 mice was released on March 1st, 2018, which we can take to be n of 0. And then 2 years later, we'll call that n of 2. That's going to be equal to 1,200. It says so right here. And then what other information do we have? We know the carrying capacity is going to be 5,000. And then, let's see. And then we're looking for time equals 7 years. I'm pretty sure that's all the information we have. Oh yes, and this n0. This is equal to the initial population. So n of 0 is also equal to n sub 0. That's a bit of a clarification. But let's see if we can use this to solve for, our constant r, and then we can just plug in time equals 7. So I don't want to solve this by hand. So I'm actually going to go to my calculator and see if we can solve this over here. So I'm going to use our second time at time equals 2. Let me see. At time equals 2, so n of 2, which is 1,200, equals, and let me set up this fraction, control divide. It's going to be the initial population times the carrying capacity, which was 1,200, or was it 1,200 or was it 5,000? 5,000. So 100 times 5,000, and then divided by the carrying capacity minus the initial population times e to the negative rt, so to the negative r times, and then t, this is after 2 years, so our time will be 2, and then plus our initial population. So if I do this and then comma r, this should tell us the growth rate. So this looks like it's going to be 1.37. So then we can just use this, but just plug in for time equals 7. So same thing. Our numerator is going to be the same. It'll be the initial population, and this is all coming from this formula, by the way. This is all coming from this formula. So for n of 7, I would just take this formula and plug in time equals 7. So time equals 7. That's all I'm doing here. So my initial population is 100. My carrying capacity is still 5,000. And then in the denominator, 5,000 minus 100 times, and it'll be e to the negative 1.36957, I'll just do that many, times the time, which we know is 7 years, because that's what we're looking for. And then always add the initial population. And hopefully this will give us a positive number for the number of years. So if I click enter, didn't really do what we wanted it to. So if I do Control Enter. Nope, it's not giving me what I want it to. It's not coming out. I don't know. Let's see. What am I doing? Ooh, I think I know what I did. I think over here I used the wrong E. This is actually pretty important. Whenever you use E, you can't just type the letter E. You actually have to go right here and use that E. So negative 1.36957 times 7. And hopefully this will give us the answer because I used the wrong E before. Yep, and so we get a population of 4,983. So let's hope that's an answer choice. 4,983, yep, that looks like it's going to be answer choice C. And so if you end up forgetting this formula, there actually is a differential equation that, there's a differential equation that when you solve it, you get this solution. So I'm going to show you that real quick. And we can use the differential equation solver on our calculator to get that. So let me show you this. The differential equation for the logistic, it's going to be the derivative of the population with respect to time. So the rate of change of population with respect to time is equal to a proportionality constant. Actually, I won't call it K because K means something else. I'll call this C. It's going to be a proportionality constant times the population times 1 minus the population divided by the carrying capacity. So this is the differential equation for the logistic model. And when we solve it, we get that equation that you saw before. So for the values that we have, dp dt, also known as just p prime, is equal to our constant, which we don't know, times the population, which is a variable, times 1 minus p over the carrying capacity, which in this case is 5,000. So if we go back to our calculator, and if you don't have an Inspire, just skip this part. I'm not sure if the TID4 has this function, but it would surprise me if it did. So I'm just going to clear this real quick. If you go to Menu and then 4 for Calculus, and down here to the Differential Equation Solver. So this is what you want to do. So our equation will be P prime is equal to our constant times the population times 1 minus the population divided by 5,000. This is exactly what I have over here. This is what I just wrote is just this. Okay? And then for the independent variable, our independent variable is time, so I'll put t. And the dependent variable, that's p, because that's the population. And we have two conditions. We know that at time equals 0, we have how many? How many do we have at time equals 0? 100, that's right. And then at time equals 2, we have 1200. So then if we click OK, oh, I did something wrong. It's actually, sometimes it doesn't work when you use two arguments. So I'm just going to use this one. So we do this, we end up with this equation. And it's a little bit harder if you don't have this differential equation solver, but it makes it doable if you can't remember the general form without the differential. So we still have to solve for c here, and that's a little bit annoying, but it's still doable. So we're basically going to do what we did before. We're going to set up a solver with this equation, and then use the point 2, 1200. Whenever time equals 2, population is 1200. So population is 1200, and the time is equal to 2. And then if we solve for c, as you can see, we still get the 1.369. This is exactly the same thing. So I'm going to define this, actually. I'll define c is equal to this. Then if I go back up here, now you can see we have p as a function of time. And so now if I define t is equal to 7 for 7 years, which is the final thing we're looking for the population in 2025, this should give us the exact same answer. So define t is equal to 7, we get p is equal to 4983. So two ways of doing it, just depends on which formula you can remember, and also if you have this differential equation solver. But yeah, at the end of the day, you get C, which is 4,983 mice. Alright, so if you have any questions from other tests, make sure to leave a comment, and I'll make a video with a solution. With that said, if you enjoyed the video, leave a like and subscribe. This has been Investigative Math, and I will see you next time.